Okay, so picture this. You are sitting in a hospital waiting room. A nurse comes over and says doctor is ready for your MRI. You get up, walk down this corridor, and then you step into a room that honestly doesn't look like it belongs to a hospital at all. There is this massive white machine sitting in the middle of the room. It looks like something out of a spaceship, not somewhere you would go to check out. A technician asks you to take off your watch, your phone, and even your ring. You lie down completely still and the table slides you inside the machine. You hear a weird whining sound and the whole thing just comes alive. It genuinely sounds like someone's drilling through concrete right next to your head. You realize that you are inside a giant magnet but nothing is actually touching you. And within a few minutes, the doctor can see your brain and even a tiny tumor hiding somewhere deep inside you without a single cut. For basically all of human history, if a doctor wanted to know what was going inside your body, there was exactly one option: open it up. And now, we just walk in, lie down, and a few minutes later, doctors are looking straight through us like our skin turned transparent. Ever wondered how does this actually work? And here's the part almost nobody knows. This mission almost didn't happen. Not because it was too hard to build, but because nobody believed it could actually work. Except for one man, who faced rejection for nearly 30 years. His name was Raymond Damadian. And weirdly enough, this whole story doesn't start in a hospital. It starts with something so ordinary, you've probably never thought about it once in your lifetime: a glass of water. Let's go back to the late 1960s for a second. Say you are a doctor and a patient walks in with brutal headaches. After hearing the symptoms, you suspect tumor. But to check it, the only real tool you had was the X ray. Great for bones, but basically useless for soft tissue. Your brain, your liver, your muscles, and your spinal cord. On an X ray, they all kind of look the same. So sometimes the only way to actually find out what was wrong was surgery. Around this time, there is this physician named Raymond Damadian who gets completely obsessed with the weird question. He wasn't just interested in treating the disease, he wanted to catch it before it turned deadly. And somehow he becomes fascinated with something almost embarrassingly simple: water. Your body is like 60% water. The brain is closer to 75%. And every single water molecule has two hydrogen atoms in it. So your body is basically packed with trillions upon trillions of these things, sitting in every organ, every muscle, and every drop of blood. And Damadian asks a question nobody has bothered asking before. What if these atoms behave differently inside diseased tissue? Now, at first, that sounds kind of absurd, right? Hydrogen is hydrogen. Whether it's in your muscle or in a tumor, the atom itself doesn't change. But here's what Damadian figured out: the atom wasn't changing, its surroundings were. Think about shouting inside a cathedral. Your voice echoes for seconds. Now shout inside a small bedroom. The echo just disappears almost instantly. Your voice didn't change, the room did. Hydrogen works the same way. The atom stays exactly the same, but the tissue around it changes how its signal bounces back. Healthy tissues give one signature, fat gives another, cancer its own. For the first time, someone had a way to maybe detect a disease without cutting anyone open. When Damadian shared this, scientists were thrilled, right? No, they were skeptical. They said it was impossible. Most people would have just walked away at this point. But Raymond went back to the lab instead. Year after year, tissue after tissue. Healthy liver, healthy muscle, cancer tissues were all compared and thousands of measurements were made. By 1971, his data was consistent. Cancer tissues really did produce a measurable different signal than the healthy tissue. In 1974, he patented the idea. Surely the funding would come now, right? No, grants never showed up. Companies weren't interested. So, if this machine was ever going to actually exist, he'd have to build the thing by himself. With just two of his students, a workshop, and literally no blueprint to follow, Damadian starts building the world's first full body scanner. Every magnet, every circuit, every line of software, invented completely from scratch. He named it Indomitable, which means impossible to defeat. And honestly, that wasn't just the machine's name, that was the man. But building it turned out to be an easy part. Nobody, not even Damadian himself, actually knew that it would work on a living human being. By the summer of 1977, after a full decade of rejection, the machine finally stood finished. It wasn't pretty. Thick steel frames, miles of tangled wire, cabinets filling up the whole room. Honestly, it looked more like a science experiment than an actual medical device. There was just one question left hanging. Would it actually work on a person? Someone had to go first. That someone was Larry Minkoff, one of Damadian's own graduate students. With no prior patients to learn from, no safety data, but with years of research and a small amount of pure faith, Larry climbs inside with fear, and the scan begins. Today, an MRI takes maybe 15 to 45 minutes, but this was 1977. The computer running the whole thing had a fraction of power your smartphone has right now. Every single signal had to be measured, recorded, and processed almost entirely by hand. Larry had to lie still for nearly 4 hours without scratching an itch, barely even breathing differently, because even the tiniest movement would blur the entire result. Eventually, the computer finishes, and on the screen appears something the world had genuinely never seen before: a cross section of a human chest. It wasn't sharp, it wasn't pretty. By today's standards, it looked almost laughably primitive. But none of that mattered. For the first time in history, doctors could actually see inside a living body without making a single incision. The impossible had just come real. And of course, one successful experiment doesn't flip healthcare overnight. The mission was still huge, slow, totally impractical for everyday hospital use. So Damadian founded a company called Phonar to actually get MRI out of the lab and into real hospitals. Scan times dropped from 4 hours down to 40 minutes. But there was still one problem. The images weren't sharp enough to pinpoint exactly where inside the body a signal is coming from. That final missing piece came from other two scientists, Paul Lauterbur and Peter Mansfield, who figured out a way to give every signal its own precise location. And in 2003, the Nobel Prize in Physiology or Medicine went to Lauterbur and Mansfield for that work. But what about Damadian's name? It was missing entirely. It's actually one of the science's most debated snubs. Did the prize belong to the guy who first believed it was even possible? Or to the men who actually made it work? Honestly, history rarely hands credit to just one person. MRI exists today because none of them ever stopped asking questions. But here's the real mystery we still haven't answered. Your body isn't made of iron. It's not magnetic. So how does a giant magnet see inside you at all? To actually answer that, we have got to shrink down way smaller than a single cell into a world that's entirely ruled by atoms. Everything around you is literally built from atoms. The chair you are sitting on, the air you are breathing, and your own body. Your body specifically has way more hydrogen atoms than any other kind, simply because it's mostly water. Scientists picked hydrogen for MRI for three different reasons. One, it's everywhere. Wherever there is water, there is hydrogen, and nearly every soft tissue in your body is packed with it. Two, it's simple, just one proton. No complicated structure, which makes its signal strong and pretty easy to pick up. 3. It tells different stories depending on where it's sitting. Hydrogen in fat behaves differently than hydrogen in muscle or hydrogen in tumor. Same cathedral echo thing we have just talked about, just happening at an atomic scale. Now zoom way in down to a single hydrogen atom. Its one proton has this property called spin. It's not literally spinning like a top. It's more of a quantum physics quirk that makes it act like a tiny magnet. So imagine trillions of these microscopic compass needles scattered all through your body, all pointing in total random directions. Their effects basically cancel each other out completely, which is the reason you're not magnetic. The scanner's magnet is usually somewhere between 1.5 and 3 Tesla. Earth's own magnetic field, by comparison, is about 50 microtesla. So we are talking about a magnet that's roughly 30,000 times stronger than the Earth's magnetic field. The moment you step into it, all these protons, which are like trillions of tiny compasses, snap into alignment all at once. Not because they are being forced to, but because it's simply the lowest energy state. Your body, at that second, becomes barely magnetized. But they don't just sit there. Even once aligned, every proton keeps wobbling around the field in these tiny circles. It's called precession, kind of like a spinning top, slowly tracing circles as it winds down. And every single one wobbles at exactly the same frequency. For a 1.5 Tesla magnet, that's about 63.87 million times a second. This is called the Larmor frequency. And honestly, it's the key to everything that follows. Because once you know an atom's exact rhythm, you can actually talk to it. Think of a kid on a swing. Push at random moments and basically nothing happens. But push at exactly the right moment every single time and the swing climbs higher and higher. That's resonance. The MRI sends out radio pulse tuned precisely to that Lamor frequency. Because timing lines up perfectly, the hydrogen atoms absorb that energy and tilt away from the field. This exact moment is called magnetic resonance. And yeah, that's literally where the name MRI comes from. The instant the pulse stops, the protons snap back to their original position, like a stretched spring letting go. And as they do, they release the energy they absorbed, not as heat, not as light, but as a faint radio signal. Fat relaxes back quickly, water relaxes slowly, and tumors often have their own distinct pattern. And those tiny timing differences are what actually becomes the contrast you see in every MRI image. But there is still one big problem left. Picture standing outside a stadium right after a championship final. 80,000 people cheering all at once. You can hear the roar loud and clear. But could you actually pick up which voice belongs to which person? That's exactly the scanner's problem. It hears every hydrogen atom in your body, but it has no idea which one came from your brain or even from your knee. And without solving that, MRI would literally just be noise. No image would ever form. So here's the solution: give every atom its own address, not a number, but a magnetic field. Inside the scanner, there are three extra electromagnets called gradient coils, one for each direction. Instead of one perfectly even magnetic field, they make it slightly stronger in one spot and slightly weaker somewhere else. Since a proton's Lamor frequency depends directly on the field strength around it, that tiny slope means every single location in your body now produces a very slightly different frequency. So the scanner no longer hears one giant undifferentiated crowd. It hears millions of individual voices, each one in its own unique frequency. The machine also works one thin slice of your body at a time, kind of slicing a loaf of bread, exciting just the hydrogen inside one slice before moving on to the next. At this point, all the scanner really has is a tangled mess of radio frequencies, basically meaningless static to our ears. Turning that into an actual picture is a job for mathematics, specifically the fast Fourier transform or FFT. Think of an orchestra, violins, drums, trumpets, all playing together kind of sounds like one solid wall of sound, but your brain effortlessly picks them apart anyway. The FFT does the exact same thing with radio signals. It separates the mixture into millions of individual frequencies, each one tied to an exact spot in your body. And the computer assembles them pixel by pixel until hundreds of these slices stack up into a full 3D image doctors can actually rotate and zoom into. Doctors can even choose which relaxation pattern to highlight. T1 weighted images make fat bright and water dark, which is great for studying anatomy, while T2 weighted images make the water bright instead, perfect for spotting swelling, inflammation, or tumors. Same exact body, just different information brought to the front. And by the way, that constant switching of the gradient coils happening hundreds of times a second is exactly why an MRI sounds like a construction site. Electricity moving through the wire inside a powerful magnet creates this physical force called the Lorentz force. And that's what makes the coil vibrate. Those vibrations are literally the banging and knocking you hear. It's also the reason why they make you take off every piece of metal before a scan. The magnets are strong enough to turn a stray wrench or an oxygen tank into an actual projectile, something radiologists call the missile effect. And since the magnet never truly switches off, hospitals are genuinely strict about what's allowed anywhere near that room. One last engineering marvel makes all of this even possible is that the magnet's coil are kept at almost minus 269 degrees Celsius using liquid helium, cold enough that electrical resistance in the coil basically disappears, something called as superconductivity. That's how a magnet this powerful can keep running for years while barely losing any energy at all. And today, AI is even helping reconstruct images from less data, while cutting scan times down even further. Plus, portable MRI machines are starting to show up in emergency rooms and ambulances, bringing this once impossible idea closer to everyone. Honestly, it all started with one scientist looking at an ordinary glass of water and asking a question nobody else had bothered to ask. Raymond Damadian never got the Nobel Prize, but every single day, somewhere in the world, a tumor gets caught early, a stroke gets identified, millions of lives saved, and millions of families thrive. All because he refused to accept that his idea was impossible. So, next time when you walk past one of those big white machines in a hospital, remember you are not just looking at a magnet, you are looking at decades of curiosity, rejection, and one question that ended up changing medicine forever. If you enjoy learning how the world's most incredible technologies actually work, go ahead and subscribe to Crazily Simple, because sometimes the most extraordinary stories are hiding inside the most simple questions.